Dr. Johannes Betz is a postdoctoral researcher at the University of Pennsylvania. He co-founded the TUM Autonomous Motor Sports Team. Within the team, they took part in the robo race competition and the Indy autonomous challenges, which they won. And as head of the research group, Intelligent Vehicle Systems, he was researching autonomous systems as the handling of limits, electric vehicles, and vehicle dynamics. And for today's talk, Johannes will discuss his experiences from robo race and the Indy autonomous challenge. And the stage is yours.
Thank you very much, and hi everybody. Just checking in with Jonathan. You can hear me loud and clearly? The audience. Okay, great. So yeah, thank you very much for the nice introduction. Today, I want to share with you how we can learn to handle an autonomous vehicles at the limit. So you had Mandur's talk before, and he introduced you to some autonomous racing. And I will go a little bit more into the depths today because in the last 5 years, I had a lot of experience with these autonomous race cars. So to better guide you through my talk, I brought 3 questions with me. And while we're having this talk, I try to answer these questions, or together in the end with a discussion, we can try to figure out if you have like additional question. The first one is called autonomous racing, autonomy on the edge. Like, why do we even want to race with an autonomous car? Like, what's the reason behind that? So I'm a Formula 1 guy since I was a child. And I watch a lot of Formula 1, MotoGP, Le Mans prototype racing. So I'm a race car guy. And if you look at the racing problem itself, you find some very interesting things if you combine that with autonomy. So in the first slide or in the first video, you see that the race car is driving on this unstructured environment. And every time a race car comes to a new environment, you have a different vehicle setup, you have different asphalt, you have different temperatures and weather. And every time the driver has to adapt to figure out what is the maximum limit he can drive on. Number 2 is decision-making at the limits. You see here an overtaking maneuver at a very famous racetrack is Spa-Francorchamps. And you see the car is doing this left-right overtaking maneuver at 270 kilometers an hour. You have high prediction uncertainty because you don't know what the other car is doing. You have to take care of strategy and energy constraints. And finally, in the third image, you see the car handling at the limits. You see Michael Schumacher driving in Monaco. You have only these small reaction times, and if you miss a spot or you miss to steer the car exactly around the turn, you will hit the walls. And if you combine all these with autonomy, you have some very, very interesting problems. And a few other people had the same idea, and they set up the so-called Indy Autonomous Challenge, where the goal is to race fully against other people. These are all the university teams that took part in that. And at the end, there was like a $1 million first prize. We had 2 races, one in Indianapolis, a single vehicle one, and 1 race in Las Vegas. The car that was given to us is the Indy Lights car. This is like a normal chassis, a normal race car chassis, but it was fully made autonomously because it was integrated GPS, a radar, a LiDAR, and a camera, and as well some computation power. So this was the hardware that was given to us. And now there was the task for us, let's drive autonomously and let's race autonomously. So now we know what racing and autonomous racing is all about. And it arises now the second question, how do we develop software for an autonomous race car? So there's a short answer. It's very similar to what you know from a normal autonomous car, but there's a long answer. You need to add some more important software modules to make the car race autonomously. What you can see here is our software architecture and our software stack that was developed from 2017 to 2022, like in 5 years, and was enhanced over time. And what you see here is the classical perception, planning and control pipeline, but with some additional modules. And in the main part of my talk, I will lead you through the software architecture a little bit more to show you where the differences to a normal autonomous driving vehicle is. And we start with the first one, it's the localization. So you know that an autonomous vehicle needs to figure out where it is in the world. In our case, we were fusing the data from GPS, IMU, LiDAR, and a specific track layout. This is very normal to what you know from a normal autonomous driving vehicle, but you see some add-ons here, especially the boundary detection and the track layout. So we were able to use this information we have gathered before about the track layout and use that in our localization technique. The second thing you see here is that the car is mainly relying on GPS. That's our #1 localization technique. In the car, we had a differential GPS, which gives us a good accuracy, but on the racetrack, we had a lot of dropouts of the localization of the GPS. So what you see here is basically a redundancy of sensor data that is used to fuse together to be accurate as possible. And I'm talking here about 2 to 3 centimeters, because less accuracy gives us less planning accuracy in the end, and that's bad for a race car. So the differences here to a normal autonomous driving vehicle is basically the LiDAR information and the track layout, which was gathered before. Then we are moving on to the second part, the object detection. The object detection is basically something that is very, very similar to what you know from a normal autonomous driving vehicle. In our object detection pipeline, we have a late fusion technique and a tracking technique that you know from the normal autonomous driving vehicles, and the pipeline is using LiDAR, radar, and camera data. First of all, when we have the LiDAR data, we were running a point RCNN deep neural network that was trained on this LiDAR data, and we're running an additional clustering and matching pipeline. With this, we have a close range detection of all the objects that are in front of us, as well as a safety pipeline when something drops out. The radar is used for a long range detection of all the obstacles, and the camera is a secondary pipeline. If we put everything together, we need to fuse, because we need to do a transformation, a plausibility check, an object matching, a state estimation, and finally a delay compensation. And if you fuse all these sensor data together in the end, you will get a unified object list that has a high accuracy detection of the other vehicles. Again, here, this is something you find in a normal autonomous vehicle. There's no special race things integrated. But now we're coming to a more interesting part. We know now where the car is, and we know where the objects are around us. Now it's getting a little bit more interesting, because now we're coming to the specific race or autonomous race components. What I show you now is our idea or our method behind the prediction of other obstacles. The highest complexity occurs when we need to correctly predict the other race cars' trajectories. Unfortunately, the current only offline trained algorithms are not considering individual driving behaviors based, for example, on the weather, vehicle type, or the personal driving style. And especially the personal driving style of one car that is like defending or is like doing overtaking maneuvers mostly on the right side is not covered. So on the left side, you see our solution to this problem by presenting an algorithm for vehicle trajectory prediction that is using so-called online learning. The fundament of that is a neural network encoder-decoder architecture that is trained offline and predicts the trajectory. What is new here is that the algorithm uses specific vehicle observations during the inference to optimize the underlying offline trained neural network at runtime. And on the right side, you can see one of the results we also applied to a normal street scenario. You see that we can predict the trajectories of 5 vehicles at the same time. And based on current observations, we retrain the deep neural network and therefore basically overfit to one specific vehicle and its driving style. With this, we have now the possibility to predict online complex opponent behavior with less uncertainty. And that's exactly what we need in an autonomous race car. Because now we are coming to the most important part of an autonomous vehicle, and that's the planning part. So everything you've seen before is very standard, or is very like adapted from a normal autonomous driving vehicle. But the magic and the heart of an autonomous race car is the planning part. Because here we decide the vehicle performance. Here we decide where the car is actually driving. And here we're running the safety assessment if a trajectory is good or not. And this part takes a little bit more time because we have a lot of components here. But firstly, I want to share with you how we can model the vehicle dynamics more efficiently and accurately to know and estimate the vehicle performance. Because we need to know in every time step what is the maximum lateral tire forces we can apply. Normally, we create a physics model of our vehicle, which are implemented with a handful of differential equations. That's what you see here on the left side. By knowing the vehicle parameters, the vehicle states, the control inputs, we can estimate the vehicle dynamics behavior for the next time steps. Unfortunately, we need a lot of parameters which need to be really accurate, and we only can approximate explicitly model effects with this physics model. So on the left side, you see now that we replace this physical model, the differential equation, with a deep neural network. We were choosing a recurrent neural network architecture as a main architecture, defined the hyperparameters and gathered data on the vehicle and in a different environments to train the network. So what you can see on the right side here is a comparison of the lateral velocity estimation from the physics model in blue and the neural network in gray. And we were able to show that with the right architecture, we can outperform the physical model, transfer easier to new environments like racetracks, and display the nonlinear vehicle behavior much better and faster. And with this algorithm, we have now the possibility to estimate the correct vehicle dynamics in every environment. And that's what we need. Secondly, by knowing now how our vehicle might behave for the next time steps, it's time for us to identify the absolute limits the vehicle can drive on. This limit can be displayed with one value only, the friction coefficient. The friction coefficient displays the contact between the tire and the road, and it's basically the value that defines for us the maximum lateral and longitudinal acceleration the car can drive on. Unfortunately, you cannot directly measure this friction value. So on the left side, you can see our approach to define this value, which we call tire performance assessment module. We were using two different software modules for that. So first, we estimate the value based on physical model and state estimation and vehicle sensor data. And secondly, we can predict the value for the future time steps by using vehicle camera and sensor data and a convolutional neural network. Afterwards, everything is fused together in a friction map. On the right side, you can see the results of these algorithms displayed in a map that has various friction coefficients integrated. This value can now be used further for the path planning and for the velocity planning. And what you can see in this image here, that we have these blue areas as low friction areas, that when we use it in the path planning, our path is completely planning around these low friction areas. For example, a wet spot, or in the middle, what you can see here is an oil spill. With this algorithm, we create a value that helps us to plan an adaptable, safe, and reliable trajectory. Sometimes people misunderstand that path planning is not the super most important part in an autonomous race car. It's the part where you get the car safe, but it's not where you get the car fast. So in this image, what I show you here is that this variable friction coefficient have a high importance for the velocity planning. So what you can see here is that with this variable friction coefficient and with knowing that this is variable, we can brake later into turn number 1. For example, we have a same trajectory in turn number 3, and we have less braking and throttle because of low friction area in turn number 3. So what you can see here is that the speed of the car is heavily depending on this friction coefficient, and we needed to calculate it correctly. Furthermore, we need this friction coefficient afterwards to calculate our global optimal race trajectory. We set up a nonlinear optimization problem, a so-called optimal control problem, to figure out what is the fastest way around the racetrack. On the right side, you can see here a comparison between a shortest path optimization, a minimum curvature optimization, and in green, the minimum time optimization, which gives us the fastest trajectory around the track. We do this offline. We run the algorithms, takes about 5 to 10 minutes because it's running a double track model for the specific vehicle dynamics. But afterwards, you get this global optimal race trajectory, and you know if you run this, you are the fastest car on the track. But ultimately, it comes down online to the car when we want to drive online. The local planning is a non-convex problem due to the multiple agents we have around us, which means for us, we need a trade-off between high-quality solution and the global optimum, and it is required that everything works along the full vehicle dynamics range. In our case, we decided to go for a multi-step approach here. First of all, we apply a local search of a trajectory with a sampling-based graph search. This is an efficient implementation, and we can set up arbitrary cost functions. And ultimately, if we found an area or found a trajectory which we say, this is a good one to overtake, for example, we do a local optimization with a tube MPC approach to refine a solution up to a centimeter level. And with this one, we can handle the disturbance and uncertainties. And just remember in the beginning, when I showed you the video of Michael Schumacher driving in Monaco, this is exactly where we can achieve this behavior. So first, the local planning is done with a graph search approach. Our goal is to drive in all environments with other obstacles around us, no matter how complex it is. This means we want to have a feasible and a dynamic trajectory that drives the car reliable and safe. So on the left side, you can see our idea of a so-called graph-based trajectory planner, which is split into an offline and online part. In the offline part, we create a state lattice and then connect each node in this lattice with splines. This basically creates a graph. In the online part, we now bring everything onto the car, and based on cost values we have created beforehand, the algorithm searches for the shortest path and plans the velocity, which gives us the correct accelerating and braking. So on the right side, you can see the final execution of this graph search in simulation while overtaking another vehicle. What you can see is the red dot is our ego car is planning dynamically around this vehicle and finally overtaking it right before the turn. And this is something you do not see with other local planners. This planner is real-time capable and was tested at a speed at 273 kilometers an hour on a real car with a maximum acceleration of 22.5 meters per second squared. And with this algorithm, it was shown that we can calculate a feasible path in complex and dynamic trajectories. And ultimately, now we know where we want to drive. It's time for us to control the car, which means to apply the acceleration and the braking commands to the vehicle. In this case, we are using an advanced version of the model predictive control approach. What you see here that in green, we are providing the car a driving tube by this local planner. We then have an uncertainty tube generated by our tube MPC. And this tube MPC helps us to have no constraint violation at all, to run faster than a normal MPC that is running with a bicycle model or even a double track model, a nonlinear MPC, for example. And we can combine the lateral and longitudinal tire limits. So what you can see here on the right side is a comparison of this tube MPC against a normal MPC and against an LQR controller. What you see here is that we set violation constraints, either in the deviation from our planned path or in the lateral and longitudinal acceleration. What you see is that the tube MPC is not violating our constraints at all, which gives us the security to actually drive exactly on the limits and not over the limits, and therefore we are not losing the car. Additionally, this setup is very, very fast because it can run at around 100 hertz, and we can reject uncertainties from the low-level controller. Ultimately, we have tested one more solution. This one made it not to the car, but I wanted to show it to you because we want to operate beyond the limits and adapt to the limits. This means we need to steer, accelerate, and brake exactly on the trajectory we have planned for. Because of control system quality and unmodeled effects, we will definitely have a gap between the planned trajectory and the driven trajectory. Since this gap is unknown and dependent on the environment we are driving, we want to mitigate this gap. And on the left side, you can see our concepts of a learning-based control approach on the method of Gaussian processes for nonlinear regression. This additional algorithm learns online while we are driving how big this gap is and then tries to close it over time. We are creating a so-called scale factor, which serves as an optimization variable to maximize longitudinal and lateral acceleration. So on the right side, you can see two examples of this version. And the plots show that the learned control error for a standard setup and a miscalibrated brake actuator using mean values in 3 sigma confidence intervals. The algorithm learns to drive the car faster each lap. It adapts with the scale factor that we can drive faster and move slowly to the set constraints while keeping the car stable. And with this algorithm, we have now the possibility to reduce the control errors while driving and adapting our controller to the environment where we are. And with this, I now finished the display of our complete software architecture to race autonomously. And of course, there might be some other approaches that you can use here too, but this is basically the results of 5 years of research, what you see here. But now we are coming to the final part. Just because we have the software ready doesn't mean it runs on the car, because now it's time for us to figure out how to improve the software for an autonomous race car. For us, one of the most components was the simulating and testing. And in the final part, I want to display the work in this field. In both videos here, you can see the exact same track, the exact same vehicle, and the exact same vehicle behavior. Once in simulation on the left side and once on the real track on the right side. By defining 2D and 3D environments, we were able to create automated software tests that evaluate autonomous driving algorithms and benchmark their behavior. The simulations are modeled on sophisticated level so that we can draw conclusions for the real world behavior. Finally, all the work I just displayed was tested on real world vehicles to evaluate, verify, and validate the developed algorithms. By connecting these individual algorithms you have seen before to our autonomous driving stack I just displayed, we were able to bridge the sim to real gap and derive more information about coupled effects in the autonomous vehicles. And that was something not many researchers can show, because sometimes you just display the one algorithm or isolated algorithms. And these algorithms, the software tools and automated tests were helped to generalize autonomous vehicle software more efficiently, faster, and ultimately better. So what you can see here in this image is our pipeline to optimize the models and the parameters in the software architecture. So you've seen all the software modules running together, but we wanted to optimize everything together. So what we have set up is a software in the loop execution on a cloud computation platform that runs our simulation environment, runs a performance evaluation, and then runs an optimization technique and gradient-free one with the NeverGrad architecture or a NeverGrad toolbox, and then optimizes model parameters based on scenarios. And just as finally 2 examples, this one here is one of the videos from the Indy Autonomous Challenge that runs the Indy simulator. And you see here now, the complete software stack of our car is running currently at 300 kilometers an hour, is running in this multi-vehicle environment, is trying to figure out its path. So with this simulation environment, we had the possibility to basically train our software, evaluate it, and made it better before we went finally and ultimately onto the real racetrack. And this video, what you see here, is now our full autonomous driving software stack running on the real car and running against another vehicle. So everything you see here now, fully autonomously, is fully racing completely alone with the software I showed you. Here, the blue car is the car from us. The white and the green car is from our components. And the goal here was to overtake each other and then increase the speed. So unfortunately, we don't have sound here, but basically the commentator is explaining that we are running up with the speeds now. And in the last overtaking maneuver, you see that the cars are going over 270 kilometers an hour. And that's quite fast, because what you see here is that the cars are doing these very stable overtaking maneuvers. It's planning the trajectory around it. It's going now to the inside, while it's on this banked racetrack of the Las Vegas Motor Speedway. And of course, the cars are just going into the circle or running into circles but it's very complicated. Now I want to pay you attention to what happens to our car. You see that the white car is moving over and our car is spinning out. So what happened here was a misdetection in the object detection pipeline. We thought the car is closer to us. We did an evasive maneuver and basically exceeded the vehicle limits. We made the second place here, but we learned a lot, and that's the last slide for today. I just want to share some open challenges with you where I think where the field is going. That's first of all the vehicle dynamic knowledge, knowing what the vehicle is doing, especially with the road friction estimation, like what is the maximum lateral and longitudinal acceleration I can apply, is very important. What I just showed you before is controlling at and beyond the limits. For example, just catching the car if it's oversteering, understeering is very difficult. Real-time capable code is underestimated when it comes to real hardware. I had a lot of people talk to me like, Johannes, have you thought about this cool algorithm? And I said, yeah, I did, but it's super slow. So it's not a solution for a fast race car. Sim to recap is a big problem, and ultimately working with real hardware, don't underestimate it. It's a lot of work to bring the software on the real car. Thank you very much for your attention. I hope you enjoyed it and got an introduction to the field of autonomous racing, and I'm happy to answer all your questions either now or later. Thank you very much.